My name is Peter Melchior. I'm from the Department of Astrophysical Sciences at Princeton University. And so this is the second time I give a talk to a pure mathematics audience. So bear with me. Most of what I say will not be overly interesting to you, but I'll promise there's some algorithms, ADMM specifically, that we use for image analysis purposes. But for the most part, you can enjoy the pretty pictures. So what you see here is an image taken with the Hyper Supreme Cam camera on the Subaru Telescope. I'll show the telescope in a bit, but I would like you to kind of take in the view. It is this is a reasonably small area on the sky. This would be about the size of the full moon, and you can see it's literally covered in like big stars like these ones here. And then smaller things, some galaxies, even some bigger galaxies like that one here. But effectively, at the depth that we can reach with modern instrumentation, the entire sky isn't dark anymore. It's effectively, we're getting to the point where wherever you look, there's something that you can see. And so if we zoom in here and it gets a little bit closer, this is still a star, but here you can see the outskirts of somewhat more extended galaxies. And despite the fact that most of these dots are pretty regular, at least at that kind of zoom level, you can see that galaxies seem to have some at least idiosyncratic, peculiar behavior. So this branch here is something that this galaxy has and others wouldn't. And you can see that in detail with all of them.
So, Peter, there might be light controls on the podium. Do you see anything?
Let's see. Not immediately. No. Hang on. No. Oh, there we go.
Yeah.
There's something, podium computer, volume, mic. If you find the light, please switch it off. All right. So where was I? I was here. All right, let's zoom in a little further, and then you can see the structures better. Then even the small things become resolved, and they're. I mean, you can see that most of them are pretty regular and smooth at those resolutions still. They're mostly symmetric, which we'll exploit. They're also mostly monotonically decreasing from the center. These will be constraints I will be putting in later on. But you can also see that there's a lot of internal structure. If we can resolve those galaxies, they have internal structure. The main problem we are faced with in images like this is that you can't find those galaxies in isolation anymore. So measurement algorithms we have on those images, they typically imply or even require that the object is isolated, but they are not. And that means if we want to measure the integrated flux over that light distribution here, then we are starting to pick up galaxies and stars that are unrelated. These are not. So what we see is a combination. Some of those things are stars from our galaxy, and some of them are galaxies at cosmological distances. But measurements of the integrated flux or the size of the object, ellipticities of objects, so kind of the 0th, the second moment of the light distribution, if you can, higher moments of the light distribution to characterize the morphology of those objects, would be contaminated by the presence of these smaller ones. So what we need is a source separation technique that allows us to analyze those as if they were isolated. So
don't worry about it, George.
No, it's all right. I'll just keep going. Just to give you a sense of the instrumentation, I'll come back to the algorithmic side in a bit, but this is the Subaru Telescope. This is on Mauna Kea, and yes, there is snow in Hawaii occasionally. This is the kind of, we're talking pretty big glass. The ring up there, this is the opening aperture of the telescope, is 8 meters across. These things are shipping containers. So these are really sizable instruments, but that's the kind of instrument we use already today and into the future with something that is in comparable size, but a much smaller and a much faster camera with the LSST is something that you may have heard. It's a big telescope currently being built in Chile. So what we have is this telescope gives us effectively something like a petabyte of data and about 1 billion or so of galaxies over the course of a year. And LSST will give something like 100 petabyte of data and dozens of billions of independent objects. So we need an algorithm that scales at least reasonably well. So we can't waste too much time on that. So what I like to do here is image analysis, but with in the way that ADMM has been used for the regularizing penalty on that, but with the twist that we need to do it on at the source separation level. There are multiple things that we'd like to tease apart. All right. So what we have in our advantage is that most of those objects, if they overlap like here, you can probably barely see this, but there's a red thing here and the blue thing here. And you can probably remember from the image I showed before, most of those objects have different colors when they overlap. And that is because they're physically unrelated. There's something in the foreground and something in the background. They share no physical relation to each other, and this is also why they tend to have different colors. But that means that in a blind source separation scheme, we can use multiple channels. In astronomy, we call them bands. So these are kind of labels. This is a bluer band, and this gets redder. And so this means that if there is a strong contamination of those two with respect to so strong mutual contamination we would have in measurements in one band, the fact that they have different emissions in different bands means that we can separate them, as you would always do in blind source separation. So one can ask the question, why don't you use something like an independent component analysis, where that would just work? The problem is this one doesn't allow for more sources than we have bands. And our bands are typically limited to something like 5 or 6. And as you saw before, we can easily have more than 6 sources in an image. So instead, what I'm doing is a matrix factorization. And that's physically very plausible. If you write it this way, you have a number of components. We assume that we know the number of components. They have a morphology, that's the distribution in the pixel space. They have a SED, that is the emission, it's spectral energy distribution. That's the emission in each of the bands, just an amplitude. And if you rewrite this sum, it's an outer product, then you get this matrix factorization. So nothing fancy happened here. But the interesting part is that relation is physically plausible. We expect even big galaxies with, say, a core and an outskirt to have a component that describes the core that has a particular spectral energy distribution and some compact emission. And then there might be others, like blue star-forming disks, star-forming regions in the disk can also be described in that idea. So this formalism is physically very plausible for us. That's kind of a nice situation. But if you look at the, as I said before, we have more components in this sum than we have bands on the other side to constrain this. So the problem is under-constrained in a pretty bad way often. So by factors of several to like, basically we may have an order of magnitude more unknowns than we have constraints from data. The data is Y here. So obviously we need additional constraining functions, one on the amplitude. So I will call this SED thing, I will call this the amplitude for the bands, and the S factor is the shape of the object. And so you can see we need penalty functions on amplitude and shape. And that is, we like to have I'm going back, we like to have the penalties on the individual factors and not on the product, because for each of them, we understand physically why particular objects have particular spectra. And we also understand, at least empirically, that different objects have different morphologies. So we can put constraints on the individual factors, but not necessarily on the product. So just here, this is an example. These are plots you would find very often in astronomy talks. I'll just walk you briefly through it. The main aspect here is this is a relation between these are basically measurements in different bands, and that's measurement in 2 other bands. And you see that galaxies tend to lie on some relation. These are sometimes called scaling relations, but the point is they're not just randomly distributed. So we know something about the distribution in this color space, so we can put constraints on each of the elements in this A matrix. These are empirical constraints. Sometimes we have even just integer constraints of saying that the sum over all bands, we just normalize that, so that we have additional constraints too. But from the physics point of view, we have constraints of that kind. And we can predict this. There are models that predict at least some of those. And we have empirical models that you can see. This line here is an empirical model for some others. In addition, also the morphology has, there's regularity in there. This is what's called the Hubble tuning fork. Goes back to Edwin Hubble, who realized that galaxies aren't all that different in terms of their bulk behavior, and identified a few different classes that are labeled here. So these are spiral galaxies with a bar in the middle. This has spiral, bar, and a different type. You can see the bar here. There's a bar structure that you see, and the spiral behavior out there. And then there are others up there that don't have a bar. And so you can classify spirals according in this, that's the fork part of it. And then there are more smooth, so-called elliptical galaxies, because, well, they are elliptical, but don't have much internal structure. The point here again is that if you think about all the possible configurations in pixel space this object could have, it must live on some pretty close and or pretty small submanifold of that possible space. And we can employ that too in terms of searching for, using manifold learning, for instance. But the point is we have constraints on those. So the constraint summary is we'd like to have sources that are somewhat compact. Independent sources are, well, sources that we can see are mostly independent, so we don't have to talk about any interrelation between them. And the constraints we would like to put on their shapes are often expressed by a linear operator, so gradients, a Fourier transform, a wavelet transform, or some spin decomposition, things that you would do with a basis transform and a linear operator. On the SCD side, we have like an integral constraint, or we project onto particular colors, or distribution of observed colors. So what we have is a bit of a hodgepodge of possible constraints that one can put. And these are independent components. So this is why I can put it as a sum. And the I goes over the different kinds of constraints I want to put on each of these. So the I is the type of constraint I want to put. The problem in astronomy is that different people want different things. So what the constraint functions are is very application specific. We would not want to impose, we don't want to have a framework in where we say the only constraint you can put is non-negativity. We would like to have, some galaxies are symmetric, some others are not. I would like to be able to put this, and as Don mentioned yesterday, I think he's left now, but you can have a very flexible mechanism of imposing those constraints with ADMM and the matrix factorization. The fact that they are independent means I can take the entire matrix, I don't have to split it into components and call it block 1 and block 2. And so this entire thing goes over just in a double sum of those different constraint functions, potentially decorated with a linear transformation matrix. Just briefly, so this is the constraint side. The objective function is just a chi-square between the two norm between, Frobenius norm between the image and the model prediction, so between A times S. But we have things like the blurring from the telescope optics in there. So you can see these are diffraction patterns. So you don't get a point source. You get some wider, think of your physics classes if you had any. Diffraction was probably covered there. So you can, this should be a point source, but it isn't. And the reason is that you have a finite aperture through which the light enters. And if the aperture is a round pupil, you get those airy rings. And you can see that the effects of different configurations gives you different effective PSFs. And then on top of that, you have the atmosphere. So if you observe from ground, you have the atmosphere doing some amount of blurring. Yep, there we go. So what you see here is a time sequence of, if you had a high resolution image of a star in the background, then these so-called speckles is what you get because of the turbulence in the atmosphere. These exposures are very short, so something like a second or so short. If you integrate longer, you get something that is more closely described by a Gaussian or a so-called Moffat profile. But it averages out and gets a rounder shape, but it gets you a substantial broadening of the image. We have to, it's a convolution, we have to fold this in. And you can by having a PSF or convolution operator P up there on the sources. On top of that, you would like to do things like occasionally have moving objects that are over here. You can see this object along this line. The track is artificial. It's generated later. It's the fit to the trajectory. But you can see this object basically moving around And you can also describe that by a translation operator in here. Occasionally, we have to account for things like that, too. Well, what you see here is this is only in the objective function. The constraints don't act on it, so it's independent. We can calculate easily gradients through that, so it's all good. So now I promised I would do, since this is a math audience, I would normally not show those, but the functional form is we have two blocks. This would be A and S in the matrix factorization, and a set of dual variables to satisfy. So this is already in the consensus form. You can see that we have those constraint functions on it. There's an arbitrary number of constraints. I don't necessarily know a priori what kind of constraint it is. So the only thing we ask is that the function that is meant, the G functions, are proximal. And the constraints are only act on one block, so they never do. They never act on x1 and x2. They're kind of treated independently. These linear operators may not be invertible, and even LTL may not be invertible. So otherwise, we could do something that in a paper by Combat and Pasquet is called SDMM that solves a very similar problem. But we have A, we have two blocks, and B, we have this condition that we don't want to require. And what we came up with in a paper with Fred Molekamp, who's a developer with me, is an ADMM-like algorithm. The stuff up there is just the initialization. This is the Lipschitz constant of the gradient. And what you get is, effectively, this is a gradient step. This will behave as a gradient step. And you get a sum over basically this difference from the dual to L times X. So very similar to what you would do in ADMM, just with multiple different duals. So for each of those blocks has a number of constraint functions on it. And for each of the constraint functions, you get a Z and a U variable. And then you sum over that. And as you can see here, we never have to invert L. Also don't have to invert LTL. So this all goes straight through. The convergence is, well, OK. So it does converge, although we don't know whether there's a formal proof that it does converge. We find it to be convergent. But the convergence could be faster, as you all know. ADMM is not the fastest. And as I mentioned before, we need speed. So we sat down and thought, OK, what else could we do? Could we do this faster? And came across a paper by this paper here. Xu and Yin, where's he? Ah. All my shout-outs go to people who have already left. Never mind. Basically, in this paper, they demonstrated that you can have a multi-block update as a proximal gradient method that you can also accelerate with a Nesterov scheme that you can accelerate by just taking the gradient step and a projection. And the only thing we do differently here that, again, I don't know if it's provably convergent, but we find it to be very effective, is that, remember, we have the sum of different G functions. And the only thing we do is using the projection on convex sets idea. Basically, we chain those proximal operators together, and that's it. We don't, so it's inexact in every aspect of it, right? We are not solving the f directly, so the objective function directly, and we never solve for the fact that this chain obviously doesn't satisfy all of the constraints at any given point. It only satisfies the last one, and so normally you would have to loop over that, and we are doing this inexactly every time. And intuitively, the reason to me that converges is that the gradients eventually will die down, and there won't be strong gradients, at which point the argument of that chain is essentially stationary, and then you loop a bunch of times to make these things all consistent so that it's feasible against all of them. Again, I'm not sure if that is provably convergent. We find it to be convergent and find to satisfy what we need. I can demonstrate how this looks in an image. This is, again, data. This is the model we get. And so what you have is a light distribution. Every pixel in here has the same color. It's just an intensity variation. But between them, they have different colors, as you can see. And the results of that compared to what we had before. So on the Scarlet is the new code that is based on this constraint matrix factorization. This is what we had before. What you see here is the measurement, the relative error on the flux of the object, so just the integrated light. And you can see that we find a substantially better and tighter relation. There's a difference between stars and galaxies because stars are just more complex and easier to handle. But you see that there's a substantial improvement that we get, and that's the quantity astronomers care about. If we can use as much compute power for achieving that as we have, so astronomers don't care about the computational complexity unless it becomes unfeasible. But so the extra cost is well justified in this particular situation because we get substantially better results. I briefly mentioned that there are different situations. So we would like to have what's called the DBlender in astronomical term. The fact that we're doing the source separation goes by that name in astronomy. What we want to use is we want it to be a framework where people can use their data or special data or some special object in the data and run their own custom analysis on it. What we've done here is instead of saying that the spectrum of all components need to just sum up to 1, we require that this component has a very characteristic spectrum because we knew what it would be. Don't ask me how we know, but we know. So we were searching for this particular color, and we were asking it to decompose that scene into a host galaxy. That's the galaxy that hosts the phenomenon that triggers this. And we would like to see that in isolation away from the host. And this is a custom constraint because the SED of that object is very distinctive. Normal galaxies don't have that. We'd like to have the flexibility in that framework to just to write a proximal operator to project onto solutions we physically understand should exist. Residual problems that we do have are of that kind. So you may see this object 19 here is detected, but that object down here, I don't know if you can see that. There's a reddish object underneath. Okay. And if you subtract the model, you can see this red object quite a bit better. And in like optimization language, what we don't know really, we have a detection algorithm that finds those things beforehand. If you think about the matrix factorization, that means we know the rank, or at least we claim to know the rank. Then you look at the residuals, and it turns out, no, that's not true. There are things in there that we hadn't detected initially. That means that we have a factorization of which we know a lower bound on the rank, but not an upper bound. And one could do something like iteratively picking up all of those things in the residuals and hot start basically everything else, or warm start at least everything else. But it would be nice if we could, if there is a way to find the rank in some coherent fashion as part of the framework in a way that we wouldn't have to iterate over, that would be very interesting. So if you have ideas, I'm all ears.
So if you just,
yep.
I guess you guessed that there were 33 objects, right?
We had an algorithm to do the detection, yes. This algorithm assumes something about what is a legitimate object. And if you have a faint object underneath a bright one, it is very likely that it would not find it as a distinct peak. So it's a peak detection algorithm that operates first. Yeah.
So if you just reran this with like k equals 34,
yep.
Would it actually looks like
there are more.
2 of them.
Oh yeah, there are more, right? The red is just the easiest to see against them.
If you reran this with a slightly higher k, would it pick out those human beings?
No, not automatically. Well, it might. What we normally do is we put it onto, like we know the component sits there and then require that it's basically monotonic about that center, right? And so if we were to allow for a component that could describe anything in here and just peaks somewhere, then this is under constraint. This is not useful, right? It will steal flux from everything, just because there's nothing I could stop it there, right? We need reasonably tight constraints, and the entire reason why we went down this SDMM-like road is because we need multiple constraints to even make this plausible.
So you would somehow process this and then pick out like a few more centers and say,
yeah.
okay, you have objects here.
That would be the customary approach here, yeah. If you have better ideas, I'm all ears again, right? So that's one of the problems we right now face is the fact that the source separation and the initial source detection cannot be split anymore because the scene is so crowded. There is a way. This is the same statement, just even worse. This is when in the underneath the point spread function, so the kind of the blurring from the atmosphere, you can't even see that there are three objects. And if you had a space telescope, which we do have in this example, then you see that there were three objects underneath. Which the solution to that is something I'm working on. I just mention it for kind of completeness purposes. We can run the entire scheme on data that comes from different telescopes. So this is ground-based data that I took a few years back, and this is the same scene observed in space. And obviously, you get substantially higher information from a space telescope, more information spatially from a space telescope, but often you have fewer filters. And so just because it is very expensive to operate a space telescope. The big laser I showed you before is very effective. That means we can afford measuring the same scene in multiple filters. And that's a kind of, this combination is something I'll be working on in the future, but it brings up again the problem that sometimes I find an object here that has no representation in the other image. And if that's the same wavelength, then it's just a resolution effect. But if these are objects in different bands, then there might be legitimately objects that only exist in a few bands, maybe in this image, but not in the other. And so what do I do about this? This is, again, a detection problem of a slightly different kind. I'll come to the conclusions here. We have data volume issues, but I wouldn't call this big data by industry standards. So this is not, if we ask Google to host this and run it, they could do it. Amazon could do too, so this is not, it's big, but it's doable. We have billions of objects, which means that we can't have too much time per object being spent on it. I didn't mention it on here. There's an additional requirement that we don't want to have systematic biases in the properties, so in the sizes of the objects we reconstruct. And so we could make errors on any individual one, but we don't want to have all of them be a bit brighter than they are, or all of them are a bit smaller than they are. That would be a problem. So we have relatively high accuracy requirements for the population. So you can't have, say, the algorithm that does the source separation do something coherently wrong to them. I mentioned this, the matrix factorization is physically appropriate. We describe as each component there would be a star or a stellar population in a galaxy, like the bulge and the disk, or the bar that I showed you. That is a physically plausible model. We found that the ADMM in this implementation of ours is too slow, or is at least substantially slower than this proximal gradient method with the chaining of the different proxies. And the detection issue is a pretty, it's an open one. There's iterative probably will work, but if there's something more coherent than that, then we don't know of it yet. Thank you.